ahead and do an example problem. Refrigerant R134A enters the condenser of a residential heat pump at 800 kilopascals and 35 degrees Celsius at a rate of 0.018 kilograms per second and leaves at 800 kilopascals as a saturated liquid. If the compressor consumes 1.2 kilowatts of power, determine the coefficient of performance of the heat pump and the rate of heat absorption from the outside air. So we have here the schematic, which is already done for us, and we can go ahead and we can draw some assumptions, starting with the fact that this is a steady, called a steady flow problem. So the problem is asking for us to determine the coefficient of performance. Now, if you remember, the coefficient of performance for a heat pump is quantified as the rate of heat rejection from the cycle divided by the work in. Now, this is the cycle that I'm circling into this boundary, right? That's the whole cycle. This is the heat that the cycle is rejecting. This is the heat that the cycle is accepting. So in order to find out what the heat rejected from the condenser is, right, that's the heat being rejected from the cycle, I should probably go ahead and do a first law analysis around the condenser. Right, so if I do a first law around the condenser, I get that this is a steady flow problem. So I'm not going to go through every single step that I used to do in chapter 5. I'm going to kind of jump ahead a little bit, but I'll explain, right? E in minus E out equals delta E system for our first law. Delta E system is 0 since this is a steady flow problem. So I'm left with energy in by heat, mass, and work equals energy out by heat, mass, and work. So the energy in, if I assume kinetic and potential energy, the energy in will be the mass flow rate of the refrigerant times the enthalpy in at state 1. That's the only energy into the condenser. What's leaving the condenser is energy by heat and, again, energy by mass. Again, if I call this 1, this is entering, and 2, this is leaving. So I get that QH is equal to mass flow rate times the enthalpy at state 1 minus the enthalpy at state 2. So I know that entering at 1, they give me the state entering the compressor. I have my refrigerant is at a pressure of 800 kilopascals and a temperature of 35 degrees Celsius. With that, I can go ahead and use ease to find out that the enthalpy is 271.22 kilojoules per kilogram. State 2, the pressure coming out is still 800 kilopascals as indicated at the outlet of the condenser. And it's telling me the quality is 0, right? That's what I'm looking at right here. That means that it's a saturated liquid. I can go ahead and I can use ease to figure out that my enthalpy exiting is 95.47 kilojoules per kilogram. So I could take those numbers and I can go ahead and plug it into the equation that I did from the first law. I know m dot, it's given to me as 0.018 kilograms per second. I have H1, I have H2. I can compute that QH is 3.164 kilowatts and I can go ahead and calculate that my coefficient of performance will be, actually I'll go ahead and on towards the top of the slide here, I'll, I'll write in the numbers. So I get QH is 3.164 kilowatts. Work in is given as 1.2 kilowatts. And the coefficient of performance ends up being 2.64. And then part B. Part B is simply asking for the rate of heat absorption from the outside air. So again, the evaporator here is absorbing heat from the outside air. So if I wanted to figure that out, I could do a few different things. I could go ahead and do a first law analysis around the evaporator, but I don't really have any information on the state of the refrigerant entering or leaving. But if I went ahead and drew my system boundary around the whole cycle, right, what I have here is energy in by heat, mass, and work, right? I have heat flow in and work in equals this heat flow out. So if I do my first law analysis, I get that the heat into the cycle, QL, plus the work into the cycle equals the heat being rejected by the cycle. Remember, this is a first law analysis around the whole cycle. And if I do my math, right, I have the work, I have QH, I can compute that the amount of heat being removed from the air, from the outside air, from the cycle is 1.96 kilowatts. All right, let's go ahead and let's try another example problem here. In this example problem, it reads that a Carnot heat engine receives 650 kilojoules of heat from a source of unknown temperature and rejects 250 kilojoules of it to a sink. Determine A, the temperature of the source, and B, the thermal efficiency of the heat engine. So let's go ahead and draw a schematic. Here I have a source and I have a sink. And I have a heat engine operating between the source and the sink. So I'm accepting Q, I'm accepting heat, I'm rejecting heat, and it's producing a net work. The amount of heat that the engine receives from the source is 650 kilojoules. And I'm rejecting heat, 250 kilojoules. It tells me that the temperature of the sink is 24 degrees Celsius. I'm going to make some assumptions. Since this process is a Carnot heat engine, I'm going to assume it to be reversible. And I'm also going to assume that this process occurs at steady flow. So part A is asking for the temperature of the source. If you remember from earlier, we went ahead and showed that for a reversible cycle, and a reversible cycle only, which this is a reversible cycle because it says it's a Carnot heat engine, the heat I accept over the heat rejected from the cycle has to equal the ratio of the absolute temperature of the hot source over the sink. I have QH, it's given. I have QL, it's given. I have TL, it's given. I can go ahead and I can compute TH to be 772 Kelvin, which is 499 degrees Celsius. Part B Part B is asking for the thermal efficiency of the cycle. Now, if you remember, the efficiency for a reversible heat engine is 1 minus QL over QH, which is also equal to 1 minus TL over TH. That is for reversible. Now, if it's irreversible, you would just use 1 minus QL over QH. But since it's reversible, you can use either one. And if you plug in the numbers, which we all have for this, we can compute that the actual highest possible efficiency for this Carnot efficiency is 61.5%. So that is the highest efficiency that heat engine can operate between two thermal reservoirs at 499 degrees Celsius and 24 degrees Celsius. Remember that in these problems, temperature is in Kelvin, not degrees Celsius. Okay, we'll go ahead and do one more example problem for this chapter. This one reads that a heat pump is used to maintain a house at 22 degrees Celsius by extracting heat from the outside air on the day when the outside air temperature is 2 degrees Celsius. The house is estimated to lose heat at a rate of 110,000 kilojoules per hour, and the heat pump consumes 5 kilowatts of electric power. Is this heat pump powerful enough to do the job? So I'll just go ahead and start off the problem assuming that this operates at steady flow. So let's look at what's going on. This house is losing heat at a rate of 110,000 kilojoules per hour. That means I must supply heat to the house at that same rate in order to maintain the temperature. Right, so that means the Q being supplied is 110,000 kilojoules per hour, or in kilowatts, it would be 30.6 kilowatts. Now that's being done by accepting heat from a sink that's at 2 degrees Celsius. And the, well, not the sink, but the low temperature reservoir is at 2 degrees Celsius, and the high temperature reservoir is at 22 degrees Celsius. Now it's asking, is this heat pump, it's consuming 5 kilowatts of power, is it enough? Now, to answer that question, we need to look at a few things. First off, how efficient is it operating at right now? What is its efficiency, right? So if I go ahead and I want to calculate the coefficient of performance of a heat pump, that would be quantified by looking at the heat being rejected from the heat pump to the space at which you're trying to heat, divided by the work it consumes. Now, based on the numbers we just found, this heat pump is providing 30.6 kilowatts of heat to the house and is consuming 5 kilowatts. It's operating, supposedly, at a coefficient of performance of 6.11. Is that possible? Well, let's look at what the highest possible efficiency this thing can operate at, right? So what we're going to do is look at the reversible coefficient of performance. If you go back into your notes for a heat pump, if you want to find out what the coefficient of performance is for a reversible heat pump, you can compute that as a function of the cold and hot thermal reservoir, right? So we found out that the cold reservoir, which is 2 degrees Celsius, that would be 275 Kelvin, and the hot reservoir was at 22 Celsius, which is 295 Kelvin. We would find out that the reversible coefficient performance is 14.75. So if you look at the coefficient of performance for a heat pump, a reversible heat pump, it's 14.75, right? And I go back and I try to compute what the work would be for a reversible heat pump. Remember, the more irreversible a heat pump is, the more work you have to put into the heat pump in order for it to do the same thing. So I'm always trying to move 30.6 kilowatts, right? So if you go back, in order to maintain the house at 22C, I have to continuously add 30.6 kilowatts of heat to the house because that is how much heat the house is losing. So the heat pump must provide that much heat. And it's saying it's consuming the 5 kilowatts of power. So that's the net work to the heat pump. But what if it's reversible, right? What would be the work in if it was reversible? Well, if it's reversible, the work in would be 2.07 kilowatts. So this is an irreversible process because it's saying that, well, it's consuming 5 kilowatts. Is it enough? And you're saying, well, in order to see whether or not it's enough, let me look at the Carnot coefficient performance and see what the minimum work that it needs in order to move that heat if it were 100, if it were as efficient as possible. And it would be 2.07 kilowatts. So basically, if the coefficient of performance, as long as it's greater than 6.11, and of course it has to be less than 14.75, then that 5 kilowatts